Welcome to video 2 of AQA GCSE Chemistry, topic 2, bonding, structure and the properties of matter. So we're going to start off with the three states of matter, and as you probably remember from year 7 there are solid, liquid and gas, and they can be represented in the particle model. Now the particles are represented by these small spheres, and these spheres could represent atoms, ions or molecules. And in a solid, the atoms are touching and are in rows. In a liquid, they are touching still, but they are randomly arranged. And as you can see, therefore, because there's spaces between, they are less dense. And then in a gas, where they are not touching and they are also randomly arranged. We also say that in a solid they are moving slowly or vibrating, in a liquid they're moving more quickly, and in a gas they're moving even more quickly. Now, limitations of the model are that they represent spheres that are solid, and of course, as you know, if there are atoms, then actually 99.999% of them would be empty space. And of course, also means that the shape's spherical, whereas many molecules, of course, are not spherical. But in terms of diagrams and drawing, it works well without overcomplicating the situation. Now, you need to know about the processes between the states of matter. So, as you probably remember, when you heat a solid and it reaches its melting point, the thermal energy is taken in and it breaks the bonds, or some of the bonds, between the particles, and it also causes them to move more quickly, so they go from vibrating to moving around each other. And then of course, as you continue to heat the liquid, some of the particles close to the surface may escape as a gas below the boiling point. We call that evaporation. And then eventually, as you continue to heat, the particles have enough energy to break the bonds between the particles and turn into a gas, and we call that boiling. Of course, some substances, such as carbon dioxide, at the right conditions, actually turn straight from a solid into a gas, and we call that sublimation. The opposite of boiling, of course, is condensing, and the opposite of melting is, of course, freezing. You also need to know about the representation of the four phases using state symbols. So S for solid, L for liquid, G for gas, and AQ stands for an aqueous solution, or dissolved in water. Now, you also need to know about the relationship between the three states of matter and thermal energy. As substances absorb thermal energy, this energy is taken in to either make the particles move more quickly or break the bonds between them. So as we heat a solid, we cause the particles to move more quickly until they have enough thermal energy to actually break some of the bonds between it, and then we have a phase change, they turn into a liquid. And then as we continue to heat, the particles will move again more quickly until of course there's enough energy to break all the bonds between them, and then it's turned into a gas. Thereafter, as we continue to heat, the particles move more and more quickly. How much energy depends on what the bonding is and the structure of the substance. The stronger the forces between the particles, the more energy you require, the more thermal energy, the higher the melting point and boiling point. Okay, you should be able to predict the state of a substance at different temperatures given appropriate data. For example, what is the state of matter of water at 40 degrees Celsius? You should also be able to explain the different temperatures at which changes occur in terms of energy transfer and types of bonding. So for example, what occurs when water reaches 100 degrees Celsius? You should say that it absorbs thermal energy, and that is used to break the bonds between the water molecules so that it turns into a gas. You should also be able to recognise that atoms themselves do not have bulk properties of materials. So for example, an individual iron atom does not have the same property as the iron bar. You should also be able to explain the limitations of the particle theory in relation to changes of state. So when particles are represented by solid, inelastic spheres which have no forces between them. So in the particle model, it looks like that the particles remain solid throughout the whole process, but of course they're not. As they melt, they turn into a liquid, and as they boil, they turn into a gas. And also, there is no sign of the forces between them in the diagram. Okay, so most of this video is about bonding and structure, and there are 3 types of chemical bonds and structures that you need to know. The first one is ionic, and I've got a summary table here which shows what the attraction of to make the bond and also where it occurs. The students have great difficulty and often mix up these two. So the first one we'll look at is ionic bonding. Ionic bonding is the attraction between oppositely charged ions. So typically we're looking at group 1, 2, 3 elements that form one positive 1, 2, 3 ions respectively, and then also a non-metal, so it could be group 7, 6, 5, or it could be a polyatomic anion, so that could be an anion, a negatively charged ion, made up of many atoms, for example a hydroxide ion or a nitrate ion. Okay, so this occurs in metals because they form positive charge, and non-metals because they form negative charges because they want 1, 2, 3 electrons to complete their full outer shell. The second type of bonding we're going to look at is covalent, and this is where atoms share a pair of electrons between them, and we represent these in dot cross diagrams and display diagrams. And these typically occur between non-metal elements and non-metal compounds. For example, the halogens form diatomic, that's 2 atoms, molecules. So they form diatomic molecules, so F2, Cl2, Br2, I2. And then the last type of structure and bonding is metallic, and this is where metal atoms are so closely packed together in these lattices that their outermost electrons that orbit the atom can actually move around the giant lattice, and we say that they are delocalized, they are able to move. And then you get an attraction between the positively charged atom, the nucleus of the positive charged atom, and the sea of delocalized electrons. And this occurs in metallic elements and of course alloys, which are a mixture of metals. So firstly, let's have a look at ionic bonding. So when a metal, such as sodium, reacts with a non-metal, such as chlorine, to complete the outermost shell, sodium loses an electron and chlorine gains an electron. And as a result, they both have a full outer shell, but the sodium, the metal, forms a positive ion because it has one more proton than electrons, whereas the negative ion has one more electron than it has protons, so it has an overall negative charge. And you should be able to show this in the formation of ionic bond, showing electron transfer using a dot cross diagram. So you represent the metal with dots and the non-metal with crosses, and in the resultant diagram you have a dot in the negative ion to show that that electrons come from sodium. So metals lose their electrons to become positively charged, non-metals gain electrons to become negatively charged. The electron transfer during the formation can be represented by dot cross diagrams. Why do they do this? Well, if you have a look, we see sodium ion's lost 1 electron, so it has a full outer shell. It's gone from 2.8.1 to 2.8. Similarly, magnesium has lost 2 electrons, so it also has a full outer shell or noble gas structure. Likewise, oxygen has gained 2 electrons to have the same structure, and fluorine has gained 1 electron to have the same structure. So formation of ions is because the atoms want to have a noble gas structure, that is a full outer shell. How do we know what charge they will form? Well, you're expected to know about the following groups. Group 1 form positive 1 because they have 1 electron in their outermost shell, and they lose 1 electron and therefore have a positive 1. Similarly, we have group 2. Group 2 form positive 2, whereas group 7 have 7 electrons in their outermost shell, so they gain 1 and become negatively charged, and group 6 have 6 electrons in their outermost shell and they gain 2. Well, you're not expected to know about the other groups. I've put group 3 in here, aluminium, gallium, indium, because they are metallics. They also form positive 3. And between group 2 and 3 we have transition metals, and they form metal ions with various different charges, and we call those transition metals for that reason. Now, an ionic compound. An ionic compound is a giant lattice structure of ions, and they are held together by strong electrostatic forces of oppositely charged ions. And I've highlighted in red the key words for the exam. This is a 3-mark question, so 1 mark for giant lattice. Second mark is electrostatic attraction of oppositely charged ions. Now, these forces happen in all directions, so in a lattice, and we call this ionic bonding. So that's the definition of ionic bonding. And the structure can be represented in a ball and stick model. So here we have chloride ions attracted to sodium ions, and because of the ionic bond being oppositely charged ions, we know that on the other side here must be another chloride ion, because otherwise it would be repelled. And what we also see in this model is that it's not, even though we say NaCl is a 1-to-1, each sodium ion is attracted to 1, 2, 3, 4, 5 and 6 chloride ions, but each chloride ion respectively is attracted to 6 sodium ions in this giant lattice. This is just a small section. In the ball and stick model, it allows you to actually see the atoms behind the front row, but of course this is a misrepresentation because there are no gaps between ions. In this representation it's better because you appreciate that there's no gaps between the ions, but of course it doesn't enable you to see first past the surface. So you should be able to draw now dot-cross diagrams for ionic compounds by metals in groups 1 and 2 with non-metals in groups 6 and 7. So pause the video and have a go at that. See if you can draw the electronic transfer in the formation of magnesium oxide or calcium chloride. You should be able to work out the charge of ions of metals and non-metals from their group number. And you should be able to deduce that compound is ionic from a diagram and talk about the limitations of using dot-cross, ball and stick and 2- and 3-dimensional models. So pause the video, have a go at that. Work out the number of empirical formula from the ionic compound from a given model or diagram. So having a look at the diagram and deducing the formula. A few properties of ionic compounds. Ionic compounds have a regular repeating structure in a giant ionic lattice with strong forces between them. So they have very high melting points and boiling points. Not only do they have very strong bonds, but as we said before, each sodium ion to turn to a gas, you need to break 6 bonds surrounding it, and similarly with the chloride ions respectively. Because they have a charge, they can also be dissolved in water, because water's polar and can actually make bonds with the ions. So actually can break bonds in the ionic substance and make bonds surrounding the metal ions and the anions. And because it's charged and because it's able to move in water or when molten, ionic substances are able to conduct electricity. So in this experiment here we have an electrolyte, that is ions present in solution, and those ions are able to carry the charge and make the light go on. Whereas if we do not have any ions, the light bulb cannot light up because there's nothing to complete the charge. Okay, moving on to covalent bonding. When atoms share a pair of electrons, they form a covalent bond. And of course these bonds are very, very strong. Covalent substances can consist of small molecules such as Cl2, or they can be very large such as polymers. Some covalently bonded substances have a giant covalent structure, for example diamond, which each carbon atom is joined to 4 other carbon atoms, and each carbon atom that is joined to is respectively joined to another 4, forming a giant covalent lattice. Or we could also have things like silicon dioxide, which is a component of glass, and as you can see here, it has a very similar structure to diamond, but it's actually made of silicon and oxygen atoms in a 1 silicon to 2 oxygen ratio. So we see 1 silicon to 2 oxygens. 1 silicon to 2. Okay. The covalent bonds in molecules and giant structures can be represented in the following ways. So we've got our dot cross diagrams that we've seen. You can have dot cross diagrams without the circles, or you can have displayed formula where a dot cross pair are depicted as a line, or you can have 3D models. Each of them have their own strengths and weaknesses. Obviously we're describing things that are 3-dimensional, so 2D representations don't give a true depiction, but of course with 3D models it's hard to see why they're joined together and what atoms are actually joined together. So you should be able to draw dot cross diagrams for the following molecules: hydrogen, chlorine, oxygen, nitrogen, hydrogen, chloride, water, ammonia and methane. So have a go at that. Represent the covalent bonds in small molecules in the repeating units of polymers and in part of giant covalent structures using a line. So try and draw the monomer and the repeating unit for ethene, propene. Describe the limitations of dot cross diagrams. So you should be able to talk about strengths and weaknesses of 2D, 3D diagrams. And you should be able to work out the formula of a substance given a model of the diagram. Pause the video, have a go at those now. Properties of small molecules. Substances that consist of small molecules are usually gases or have a very low melting point. For example, in group 7, where at room temperature fluorine, chlorine are gases, bromine is a liquid, and iodine is a solid. These substances have very weak forces between molecules. Remember, inside the molecules we've got very strong covalent bonds, but between the molecules, intermolecular forces, these are weak, and therefore if we only require a small amount of energy to break the bonds between the molecules, then they have easily turned into a gas. We are not breaking the bonds inside the molecule when we boil or melt something. That is a chemical change. Boiling and melting is a physical change. Okay, properties of small molecules. The intermolecular forces increase with the size of the molecule. So the larger the molecule, have higher melting points and boiling points. And you probably remember this from alkanes. As alkane chain length increases, their boiling point increases. But also we have it for group 7. So if we have a look, as we go down group 7, we get F2, Cl2, Br2, I2, and they get larger. So this is a graph of atomic radius. We also see that their melting point and boiling point increase. So the trend of melting point and boiling point is as you go down group 7, they get larger because the molecule size is getting larger. Now these substances do not conduct electricity because the molecules do not have an overall charge. Polymers. Polymers are very, very large molecules, and the atoms within the polymer are the intramolecular bonds, are very strong covalent bonds. And the bonds between the chains, these are intermolecular forces, and these are very weak, as we've seen before. But because the chain's so long and we have so many intermolecular forces, the strength in polymers means that the resultant forces between the chains is also very large. So these are very strong intramolecular forces. these are very weak in turn, but in a long chain there are so many intermolecular forces, the resultant sum of all the forces means that the strength is large. Right, okay, so that's covalent. You should be able to use the idea of intermolecular forces are weak compared to covalent bonds to explain the properties of simple molecular substances. And you should also be able to recognise polymers from diagrams showing their bonding and structure. Giant covalent structures. Substances that consist of giant covalent structure are solids with very high melting points and boiling points. For example, silica, SiO2, diamond and graphite. Now in these cases all of the atoms in these structures are held together by strong covalent bonds. There are no weak intermolecular forces in diamond, and therefore these need to be overcome by breaking the covalent bonds between it, so it requires a lot of energy. Diamond and graphite are forms of carbon, and silicon dioxide or silica are all examples of giant covalent structures. Diamond, first of all. In diamond, each carbon atom is joined to 1, 2, 3, 4 other carbon atoms using strong covalent bonds. So diamond is one of the strongest and hardest substances known to man and has a very high melting point, and of course cannot conduct electricity because it has no delocalized electrons to carry the charge. However, in graphite, each carbon atom is joined to 1, 2 and 3 other carbon atoms by strong covalent bonds. Now this means that it also has a very high melting point, very high boiling point, and can be very, very strong because you need to break these bonds within the layers. However, its fourth electron is delocalized between the layers, which means that it has delocalized electrons which can carry charge, so graphite can conduct electricity, and it also means that it has weak forces, intermolecular forces between the layers, which means that it can be used as a lubricant because these layers can slide off quite easily. And that's actually what's inside a pencil lead. It's graphite, and when you put force on the tip of the pencil, individual layers of graphite slide off, and that's what the representation of the picture means. So the important part about graphite when comparing it against diamond is that each carbon atom forms 3 covalent bonds and the fourth electron is delocalized. Now, graphene is a single layer of graphite and has properties that make it useful in electronics and composite materials. That's materials made of 2 or more other substances. Fullerenes are molecules that are made of carbon that are joined up in hexagons and pentagons which look like footballs. The structures of fullerenes is based on hexagonal rings and may contain rings with 5 or even 7 carbon atoms. The first fullerene to be discovered was the Buckminster fullerene, which is made of 60 carbons and has a spherical shape. We can also roll up a sheet of graphene to form a nanotube, which has a very high length to diameter ratio and is also very, very strong. These make these properties useful for electronics because inside the tube flow electrons with little or no resistance. Okay, you should be able to explain the properties of diamond in terms of its structure and bonding, and also graphite, and also know that graphite is similar to metals in that it has delocalized electrons and therefore can conduct electricity. You should be able to recognise graphene and fullerenes from pictures in the exam and describe their bonding and structure. You should be able to give the uses for fullerenes, including carbon nanotubes. Last one we're going to talk about is metallic bonding. Metals consist of giant structures of atoms arranged in a regular lattice structure. The electrons in their outer shell of the metal atom are delocalized and therefore are free to move around the giant lattice structure. The sharing of delocalized electrons gives rise to strong metallic bonds because it's the attraction between all of these electrons and the atom itself. Metals have a giant structure with strong metallic bonds. This means that they have very high melting points in pure metals. They are also malleable, and it means that and ductile, and it means that they are also sonorous, which means that they can conduct sound. Pure metals can often be too soft, and therefore a mixture of metals are added to make what's called an alloy, which actually disrupts the regular structure and makes them harder or stronger. Metals are good conductors of heat and electricity because the electrons are delocalized and therefore can carry charge through the metal. And also thermal energy because heat energy can be transferred because the atoms are closely packed and the delocalized electrons can actually help transfer the energy. Okay, you should be able to explain why alloys are harder than pure metals in the fact that they disrupt the layers of atoms in their structure. Sizes of particles. You also need to know about nano science. So here's a scale of size of a tennis ball, full stop on a page, cells in a body, a virus, a glucose molecule, an individual atom. And the nanoscale is basically from small to large molecules. It refers to structures that are 1 to 100 nanometers in size. A nanometer is 1 times 10 to the minus 9, so a billionth of a meter. Nanoparticles are smaller than fine dust particles and much smaller than coarse particles like dust or sand. What's interesting about nanoparticles is that as you decrease the volume, the surface area increases. So if you decrease the volume by a factor of 10, so 100 cm cubed by 100 cm cubed by 100 cm cubed goes down to 10, the surface area actually increases. So to volume ratio. So actually the surface area volume ratio actually increases by a factor of 10. And because reactions happen on the surface of chemicals, you actually get many more reactions for the same volume that you've used. So nanoparticles in their size may actually have properties that are different from the same bulk materials. This also means that smaller quantities are needed and actually reduces cost. So uses of nanoparticles can be in things like medicine, electronics, sun creams, deodorants and catalysts. A new application for nanoparticulate materials are important in areas of research. So this nearly concludes the video. You should be able to compare nano dimensions to typical dimensions of atoms and molecules, give appropriate information and evaluate the uses of nanoparticles, and explain why there might be possible risks for new nanomaterials.